Hello, today I reviewed the paper accepted in NIPS 2018. The title is Beyond Grid Learning Graph Representation for Visual Recognition. This paper focuses on semantic segmentation, object detection, and object instance segmentation. The objective of semantic segmentation task is to predict the class label of each pixels from input images. And the purpose of object detection and instance segmentation is to detect bounding boxes of the object from input images and segment the object from boxes. Deep convolutional networks have been successful for visual recognition, and these deep models stack many local operations of convolution and pooling. This stacking not only provides strong model for local patterns, but also creates a large receptive field to capture long-range dependencies. In this paper, instead of deep stacking, they propose a novel approach for capturing long-range dependencies using deep networks. They propose learning graph representation from 2D feature maps. The vertices of the graph define clusters of pixels called regions, and edges measure the similarity between these clusters in a feature space. This graph representation learns to propagate messages across all vertices on graph to share global information. Also, this graph representation facilitates reasoning beyond regular grids and can capture long-range dependencies among regions. Before explaining this paper, we'll look some basics and terminology for graph data. The graph consists of two tuples of V and E. The V is set of nodes, and E is the set of edges between nodes. Also, we can define the adjacency matrix A in this way. When the nodes are connected in some ways, the elements of adjacency matrix will be 1, otherwise 0. It can be also weighted form if you want to consider connections differently. These adjacency matrices represent the relationship between graph structures. And now I'll explain the proposed method in this paper. The method consists of 3 operations: graph projection, graph convolution, and graph reprojection. First, graph projection turns a 2D feature map X into a graph, where pixels with similar features are assigned to the same vertex. The outputs of graph projection operation are the pixel to vertex assigned matrix Q that represent that pixels of feature maps are assigned to which vertex of graph representation. And vertex features with Z means node features, and also adjacency matrix A from vertex features G. Second, graph convolution makes use of convolution on graph structure and update vertex features based on the adjacency matrix A. In this paper, they use graph convolution network, which is proposed by Kiff et al. In ICRL 2017. Third, graph projection interpolates the vertex feature Z tilde into a 2D feature maps X tilde by reverting the pixel to vertex assignment matrix Q from the graph projections tab. And finally, we can get the final 2D feature map X tilde from feature map X with the graph convolutional unit. So I'll explain the details of graph projection. Graph projection assigns feature map X to a set of vertices parameterized by W and sigma. Each column WK means the anchor point of the vertex K. We can consider the column WK of W as mean and the column sigma K of sigma as variance of cluster K. For example, the number of vertices can be predefined. So in this slide, we assume the number of vertices is 4. The graph projection computes assignment matrix with this formulation. This computes weighted Euclidean distance between all xij and wk and creates soft assignment using softmax function. In this paper, for stable training, they initialize the W and the sigma in graph projection operations by using k-means clustering. They use k-means clustering to get the centers for each column wk of W and also estimate the variance along each dimension and set up the column vectors sigma k of sigma. Then we can encode vertex feature zk for each vertex by this formulation. Each gk prime is a weighted average of the residuals between feature vectors xij and to the vertex parameter wk, and we use L2 normalization to zk prime, and we can get the gk. Also, we further compute the graph adjacency matrix as A equals Z transpose Z with normalized zk. An element of adjacency matrix A is the pairwise cosine similarity between the feature vectors zk and zk's. So by graph projection, we can get the assignment matrix Q and the vertex feature Z and the adjacency matrix A. After graph projection, we can get the output as the vertex feature Z and the adjacency matrix A. The graph convolution takes the inputs of vertex feature Z and the adjacency matrix A and produces transformed vertex features Z tilde. Then we make use of graph convolution operation proposed by Kith et al. In ICRL 2017 to propagate information on the graph. The function f can be any nonlinear activation functions. In this paper, they use the batch normalization with ReLU. So, we can get the transformed vertex features Z tilde from graph convolution. Finally, graph reprojection interpolates the vertex features into 2D feature map by reverting pixel to vertex assignment matrix Q from the graph projection steps. Graph reprojection operation takes the input of transformed vertex features Z tilde and the assignment matrix Q from the graph projection step and produce the 2D feature map X tilde. Ideally, we have to invert the assigned matrix Q, but this is infeasible. Instead, we compute pixel features of X tilde using a reweighting of vertex features Z tilde. Thus, graph reprojection interpolates 2D pixel features based on their region assignment. Even if two pixels are assigned to the same vertex in graph projection, they will have different features after graph reprojection. So finally we can get the 2D feature map x tilde from 2D feature map x by graph projection and graph convolution and graph reprojection. Proposed graph convolutional unit also can be easily wrapped into a graph block and incorporated into an existing network. They suggest two types of graph blocks. First, a residual connection from input feature map. Second, concatenating features supplement the original feature map X with global context captured at different number of vertex. They use this residual connection with a single GCU for object detection task and instance segmentation, and concatenate features from multiple GPUs for semantic segmentation. To verify the effectiveness and performance of graph convolutional unit, they perform experiments on three tasks: semantic segmentation, object detection, and instance segmentation. For semantic segmentation, they use concatenation of multiple GCU outputs. They use ADE20K dataset for semantic segmentation. They concatenate the outputs of 4 GCUs, and GCUs have 2, 4, 8, 32 vertices, and output dimension is 256. Their results are summarized on this table. GCU improves the performance from other baseline models. In pixel level accuracy, the performance is consistently lower than PSPNet. One possibility is that GCU will produce diffused pixel features. This is because the output features of GCU are linearly interpolated from region features. In this figure, we can see the missing clock in the left column because of oversmooth by linearly interpolated from region features. For object detection and instance segmentation, they incorporate GCUs with residual connections into the Mosk-RCNN framework. They use COCO dataset for object detection and instance segmentation. Their results are summarized in the table. GCU improves the performances from Mosk-RCNN for both detection and instance segmentation. One of the failure modes of GCU is the missing detection of small, out-of-context objects such as skis in the sky. This is again due to the diffuse local features in GCU. Now I summarize this paper. They present a novel deep model for learning graph representations from 2D visual data. The proposed graph convolutional unit transforms a 2D feature map into a graph structure by graph projection, graph convolution, and graph reprojection. This graph structure has vertices defined in regions and edges capturing the relationship between regions. They also provide a revisit to the region-based recognition in the era of deep learning, and they offer useful insights in rethinking the design of visual representations in deep models. Thank you for listening.